Hello and welcome to today's episode of Kitchen Physics. I'm your host, Amanda. I'm a CPA by day and a foodie by night, so why am I doing physics? Well, there's nothing like a challenge. And I've got some fascinating physics happening at my kitchen table today, so let's get started. Today's physics experiment involves an object moving at a constant speed. I've taken a video of the motion of the object and subjected it to video analysis. I've also written a computer program to model my expectations about the object's motion. Then I've compared the actual results to the modeled results, with some interesting differences, as we'll see in a minute. I set up the experiment in my kitchen because the floors are uneven in my house, so the kitchen table is the closest to a level place I could find. More about that later on. I chose an empty tea tin for my object. I used a measuring tape for calibration because my old wooden meter stick turned out to be just a yardstick with no SI units on it. And then I asked my handsome assistant to roll the tea tin in a straight line along the measuring tape. In the tracker software, I selected the portion of my video that showed the tea tin rolling at a constant speed, at least to the naked eye. I selected the axes to have the plus X direction toward the right side of the picture, the plus Y direction toward the top of the picture, and the plus Z direction coming directly out of the picture. I set the origin at the tea tin's average initial position, and I chose the time interval to be the same as the frame rate of the camera, which was about 0.042 seconds. I calibrated my video by using 2 of the darker inch markers on the measuring tape, because after I went out to the garage and got a measuring tape with centimeters marked, the centimeter marks weren't focused enough to use. I'll have to work on that some more for the next episode. But don't worry, in my analysis, I carefully converted my 1-foot calibration stick into 0.3048 meters just to make sure I used the proper SI units. I wrote a computer model of an object in constant motion to provide data to set my expectations about the results of the experiment. To create a computer model utilizing Newton's second law, I needed to enter the initial position, the initial velocity, and the object's mass. I weighed my tea tin in my kitchen scale and entered its mass into the program. I entered the initial position as the origin. I calculated the initial velocity by using my first 2 experimental data points and entered it. For purposes of this particular computer model, I could assume that net force was 0, because this is a necessary assumption in order for my object to be moving at a constant speed. I set the time interval equal to the camera's frame rate. I set up my computer program to run iterative calculations of the object's position and velocity based on Newton's second law and the values I'd already entered. I programmed the computer to place the results of its calculations into a data file so that I could analyze them later on. The data file contains the timestamp and the calculated x-coordinate for each data point. I also cut and pasted the timestamp and x-coordinate for each data point based on my video analysis into the same data file, side by side with the calculated results. I used a spreadsheet program to create a line graph to compare my experimental data with the data produced by my computer model. The green stars mark the actual position of the tea tin, and the blue line marks the calculated positions according to the computer model. As you can see, the graph of the actual results diverges pretty significantly from the calculated results. I attempted to explain this away by blaming air resistance, friction, and the weight force. Those seemed like reasonable culprits since we haven't learned to model those yet. But those would have caused the tea tin to go less along the x-axis than I predicted, and my results showed it going more. Back to the drawing board. How about the motion along the y-axis? My handsome assistant probably didn't roll the tin exactly straight. In fact, I know he didn't, so that some of its motion was along the y-axis. But again, that would explain less x-axis motion, not more. I finally concluded that my measurement of initial velocity must not accurately represent the constant velocity of the tea tin. Remember those uneven floors? My experimental results indicate that my tea tin was actually speeding up as it rolled slightly downhill on the table. I've really got to get those floors fixed. Were you curious about the one green star that's way at the bottom of the graph? No, my floors aren't that uneven. My camera just missed a frame. So the moral of the kitchen physics story today is, once you consider air resistance, weight force, friction, crooked rolling, and crooked floors, It's just not that easy for a CPA to get an object in constant motion in the real world to look just like a computer model. Oh, and in case you were wondering, green tea isn't just handy for doing physics with its packaging. You'll get the best tasting cup of green tea by steeping it in barely boiling water for only a minute. It won't be bitter, and you'll still get all of the great health benefits of drinking green tea. Thanks for watching, and I'll see you next time on Kitchen Physics.